Hey Honors Physics, this is Mr. Hausman, and now this is the fourth lesson in the series on electric fields. This one's all about the numbers, all about the quantifying charge. So turn ahead to page number, let's see, which one is this? 17. We're going to be looking at 17. So back on page 17, okay. So what's the fundamental challenge here? Well, the final step in this chapter is to start to measure how strong is the force of a charge that's in an E field. How much force does it experience? And there's different applications. One's a photocopier, one's an old-fashioned TV. And I know these feel like pretty weird applications, but E fields are in a lot of technologies. They specifically put the toner or the ink on the paper in a photocopier. And in an old-fashioned TV, the kind that used to have a tube behind it, it actually steered a beam of electrons. Electric fields would steer the electrons, they would hit the screen, and that would cause your screen to give off light or color. So I grew up with those, but of course you've probably grown up with flat panel TVs, which work very differently. So let's begin. So a piece of ink, or the proper name for it is toner, because it's a powder, it's actually dry, but it is incredibly charged. So remember, a single electron is to the negative 19th power, but we have a pretty large charge, 4 times 10 to the negative 9th coulombs. That's a negative 9, okay? It's still small, but it's not as small as an electron. And it is redirected or pushed by an electric field. The E field is how big? 1.2 times 10 to the 6th newtons per coulomb. Much bigger than the fields inside a lightning cloud, for example. So how big is the force? So the formula is Fe, that's the electric force, is the product of the charge times the E field, 4 times 10 to the negative 9th coulombs. And we're going to include our units because the units are not that bad. 1.2 times 10 to the 6th newtons per coulomb. The coulombs cancel, and you're going to get a force. So let's hit pause and try that. Hopefully that was enough time for you to take out your calculator, and I got an answer of, oops, let's not use the eraser. The force is 0.0048 newtons. That's a pretty modest force. That means not too big, not too small. But we're going to find out in the next page that that is actually a huge force if you're talking about very small masses. So it may not feel it, but that piece of dust or toner that's black that gets pushed on the page where the ink is being printed is actually accelerated at a huge rate. But we're going to focus on just the forces for now. So the next one is an electron in a TV. And you notice that there's only one piece of given. There's a force given. So let's write that. What force is it? It's the electric force. We know that because it's a field creating it on a charge. 3 times 10 to the negative 6th newtons. And you notice there's nothing else. Well, I expect you to be able to pull out the fact that the charge of a single electron is 1.6 times 10 to the negative 19th. When I say pull out, we've used that a lot. That's the elementary charge. I mean, you at your table or your group of students you're working with, someone knows that value. And I will give you reference sheets, but that's a known value, right? We know the elementary charge of an electron. So now, can you rearrange that formula? So I believe that we're going to take, to find the E field, we're going to take the force and divide it by the charge. So 3 times 10 to the negative 6 newtons divided by 1.6 times 10 to the negative 19th coulombs. Now notice I dropped the negative sign. That's not a mistake. That's because we don't know the direction of the E field. In fact, the E field in a TV was always changing direction. They would change the two metal plates from positive to negative and vice versa, and it would cause the electron to sometimes be pushed toward the top and be sometimes pushed toward the bottom of the TV. So we're really just finding the magnitude of the E field. Hit pause and try this, see if you can get the answer that I get. And now you're back, 1.875. This is without regard to sig figs for the moment, but look how big the E field is, to the 13th power, so enormous. We also tried number 4. Try number 4 where we are given a force and we're given an E field. What's the charge? Hit pause, see if you can do that problem from scratch using Q is equal to force over E field. I got a value of 7.78 times 10 to the negative 9th coulombs when I plugged in my force, when I plugged in my E field. So that's my Q value. Now, we finished that lesson with a question that says, well, if that's my charge, how many electrons or protons is that? And we found out that the charge came out to be a positive number, so I guess we're going to be focusing on how many protons is in this much charge. And you could use simple dimensional analysis to do that. So we're going to use that thing called the elementary charge now, and we're going to recall that essentially we know that one proton has a charge of 1.6 times 10 to the negative 19th coulombs. So if you cross multiply, do a little dimensional analysis, you'll essentially get the fact that there's 4.86 times 10 to the 10th protons in that charge. That's how many protons, I ran out of space, sorry, that says PO, protons should be holding that charge. So that's page 1. They were pretty easy. We're going to be looking at 18 investigation, like level 1. The next step is we're going to combine them, that is to say the formula that we just practiced with an old formula to do things like find the acceleration. So for a typical charge, right, that's in an E field, here's a Q and it's in an E field, okay, right, left, up, down, it doesn't really matter. We know that it gets pushed and we know how to find that force. And we're going to find out that essentially that force is actually the same as the total force because, sorry, little stutter there, because the force of gravity for very small particles like single electrons does not exist. Essentially what we're going to do is we're going to find the force equals Q times E. We know the charge of an electron. We know the E field, right? There's the E field. So we've got 1.6 times 10 to the negative 19th coulombs. That's my Q. My E field is 3 times 10 to the 6th newtons per coulomb. Cancel coulombs. And you get a force, right, that is equal to 4.8 times 10 to the negative 13th newtons. And you're like, that's so small it doesn't matter. That can't be important. Well, when you then use Newton's second law and you say the sum of the forces on that matter, even though it's an electron, is equal to its mass times its acceleration. And the question here is, what's its acceleration? So we're using new physics with some older physics. And the force, the electric force, is the total force because gravity is inconsequentially small. It's too small to matter. Now, no one has this memorized, but the mass of an electron, well, someone does, not me, 9.1 times 10 to the negative 31st kilograms is the mass. And then there's the A. So we're gonna, oops, there's the A. So we're gonna divide both sides by the mass, and our acceleration comes out to be 5.27 times 10 to the 17th. That's positive 17th meters per second squared. Yes, subatomic particles accelerate with accelerations that are so many times bigger, billions upon billions of times bigger than what we think is a big acceleration like gravity, like being in free fall. Now, in class, we asked everyone to then try number 1 and 2 and 3 for homework. So I don't want to show all of those, but perhaps just to make sure we're off to a good start, some people had trouble with what's an alpha particle. And it says it's 2 protons and 2 neutrons. Well, we don't care about the neutrons. They don't have any charge. But if it has 2 protons, then its Q must be double the elementary charge. And I can double 1.6 in my head. If you can't, just double 1.6 and you get 3.2 times 10 to the 19th coulombs. And what would be the force? Well, then we're going to use force equals QE. And then you're going to do the same step where you use the sum of the forces equals the M times the A. And the mass is given, right? The mass is given up in the problem, 6.64. And that's where a few people had trouble. They had trouble not with the mass, but figuring out the charge. And a couple people asked about it in class, which was excellent. So the bottom of the page doesn't seem to have two steps. There's no part A and B or part A and C. And that's because, here's what I encourage. What if you start with this statement? Haven't we been doing that where we take the answer to part A and then setting it equal to the force? So now what you can do is you can do double substitution, and you can solve these in one step. By plugging in 3 values, you can find the missing. So they weren't that bad. Let's see if you can give it a try. Turn in page 18 and 19 for homework, okay? Page 18 we're on right now. And then we're gonna be looking at 19. And in particular, page 19 is about the Millikan oil drop experiment, which leads us to our lab. Lastly, Millikan. Okay, we watched a video in class. Robert Millikan, American physicist, first to win a Nobel Prize from the United States. What did he do? He discovered this charge. It wasn't known. In 1909, that charge was being discovered. A guy named J.J. Thomson, you probably heard about him from chemistry, he discovered what was called the charge to mass ratio. He didn't know either one, but he knew how big one was compared to the other. Okay, it's 100-year-old physics, so we're not going to revisit all of it. So Millikan said, well, I can come up with a special machine, and this looks large, but it's actually quite small, and it basically took oil droplets, dropped them into an electric field, and the electric field had a positive plate on the top and a negative plate on the bottom, and we know that that creates an electric field. And an oil droplet that gets sprayed into the top, a stream of them would fall into a little hole, right? See the little pinhole in the top plate. And in doing so, the oil droplet would become charged. Now, it's a little more complicated. They use X-rays, it ionized the air made the oil charged, but ultimately the droplet of oil became negative. And suddenly now, that oil droplet feels a new force. It obviously feels the force of gravity, but now it also feels an upward force. And depending on how strong the E field is, Robert Millikan figured out a way to make those oil droplets hover. Well, what's the big deal about hovering? Well, that's in equilibrium. If the droplet doesn't accelerate downward, it just stays in place, then we know that the electric force must be equal to the magnitude of the gravity force. So do you see the connection to the previous page? All we're doing is now doing a new equilibrium. So the drop was negative, and the way we know that is because, right, how do we know it's negative? It acquired, right, how many electrons? Well, you haven't read this one yet, but read number 1, and you're going to find out it acquired 6 extra electrons. That's how you make it negative. What direction is the E field? Now, this is a trick, or it's a little tricky. Look at the plates. The plates were positive on the top and negative on the bottom, so the E field is actually downward because it goes from positive to negative, right? That's the direction of an E field. It comes out of a positive and into a negative. So what E field is needed to suspend the droplet? It certainly doesn't look like there's enough room to do any work here, but let's start. The electric force is equal to the force of gravity for all Millikan problems. So therefore, Q times E equals M times G. Double substitution, the formula for the electric force, the formula for the force of gravity. And 6 electrons means that that's 6 times 1.6 times 10 to the negative 19th. I could do that out, but that's my Q. My E field is my unknown. The mass of the droplet of oil is given. He knew how to measure that. And then G is just 9.8. So with a little multiplying and then simplifying to get the E alone, don't forget you need to multiply that 6 times the E field, 6 times the elementary charge right here. You're going to get an E field of 33,000 newtons per coulomb. And you're going to try the other 2. So not as much lead in. We're not going to do 5 practice problems. We're just going to do 1. By the way, that answer actually comes out to be 32,666. And so now we're rounding. So there's the last lesson in the unit, a little quantification of forces and fields connected to charges.